Okay, so last week I started talking about electric charge and static charges in particular, where you just have plus or minus charges that are staying in one place. They are static. Now we're going to talk about charges that can move, and the flow of electrons through a wire is known as electric current. And it's something that just keeps going as long as you have what we call a circuit. Now, it's not like water moving through a hose. A hose is hollow and actual water molecules are flowing in one direction through a hose. In a wire, the electrons, the free electrons, move along the outside of the wire. And they don't just move in a nice smooth path like water through a hose does. Rather, they move in this kind of zigzagged pattern. That's what the path of an electron would look like as it goes through a wire. Now, we measure current as how much charge is moving past a certain point in a given amount of time. We measure it in terms of coulombs per second. And the metric unit, or the unit that we use that is the same as coulombs per second, is an ampere. So currents can be very dangerous. If you have a high current that can run through your body and it can stop your heart, or it can mess up your brain or your nervous system, 0.1 amps, a very small amount of current, if you get that running through your body the right way, that can kill you. Not to be too dark. But electrons, why do they flow in the first place? So let's say we have two batteries here. Okay, both of these are 1.5 volts. All the batteries you buy at the store that are AA's or single A batteries, or C batteries, or D batteries, the ones that look like this, they're all 1.5 volts. So what does it mean to have voltage? Basically, it's creating a hill for electrons to flow through. Now, these electrons want to get up here to be with these protons because they're attracted, but there's stuff in here that basically prevents that from happening. But if you touch a wire to the negative end of a battery, and you then touch that wire to the positive end of the battery, now they have an easy route to flow. They can fall, so to speak, downhill, even though they're not necessarily falling. So the bigger the battery you have, the more stuff you have that can fall, but the size of the hill, or the size of the fall that they're going to create, is the same. It's just that these have a lot more charges that are going to be able to flow. And electrons in a circuit like this, in a wire, flow from the negative end because they don't want to be with the other negatives. They fall from negative to positive. All right, so if you want to give those charges more energy, you can create a higher voltage. Voltage is sort of a hard thing to understand. Basically, you can kind of think of it as like an electrical push through a wire. Even though it's not a force, it has similarities to force. And so for now, you can just kind of think of voltage as being that. Now, every wire and every electrical device that you have has something called resistance. There are things that are basically trying to stop the electrons from flowing, and copper, gold, and silver do a very nice job of letting electrons flow. That's why we use especially copper in our wiring. And then, things like insulators prevent those electrons from flowing. You don't have to spend a lot of time remembering this, but the longer a wire is, the more resistance you're going to have, which means that you're going to have lower current. Resistance keeps the current low. If you have a really thin wire, you have a really hot wire, those wires also will have a high resistance and lower currents. Dry human skin has a resistance of about 100,000 ohms. Wet human skin has a lot lower resistance. So you're much more susceptible to getting an electric shock or being electrocuted when your skin is wet. And that's the currents can be much higher because there isn't as much resistance there. This is something called Ohm's Law. Again, you're not going to have to really know this, at least this year. But basically what this is saying is that if you have a certain voltage, what's going to happen to your current if your resistance increases? Well, if this R gets bigger, I has to get smaller, and vice versa. If R gets smaller, if you have less resistance, less things stopping the current, you're going to get a bigger current. All right, and finally, we've got electric circuits. So a circuit is any path through which electrons can flow. And so I showed you a few other examples, but here we've got wire leading from plus, it's going to, and then one from minus. Electrons actually are going to flow through here up into the light bulb and then come back. Now, there are two basic kinds, and again, we're not going to spend a ton of time remembering this, but we'll do a lab activity today that's going to kind of let you play around with some of this. But basically, there are two main kinds. You've got series circuits, which means that there is only one pathway for electrons to be able to flow, and they have to go through every device. So in this situation right here, if I unscrewed this light bulb, the circuit would be broken and nothing would work. Okay, this light bulb would turn off too because there's basically the bridge is out and you can't keep the electrons moving. This right here, this is called a parallel circuit. And here you're going to have the electrons. Some electrons they're all going to flow through here, but then some of them are going to go through this light bulb and then back to the battery, and some of them are going to bounce around and come through this light bulb and then return to the battery. In this case, if I unscrew this light bulb, they still have a path to be able to get around back to the battery. Or if I unscrew this one and keep this one screwed in, they can just go around this way. So as long as there is a connection from this end of the battery to that end of the battery that isn't broken, you can have a working circuit. And again, one pathway is series, more than one is called parallel.